In this video, we're going to start looking at how we count things as chemists, which doesn't really sound very exciting, doesn't really sound like a new concept, but in chemistry, we face a kind of unique issue in that we deal with atoms and molecules, which are incredibly small. So even what looks like a small quantity of something, a spoonful of a substance, a handful of a substance, contains absolutely massive numbers of particles. So we are constantly dealing with very, very large numbers of very, very small things. So it becomes impractical to actually count them one by one. If we want to know how much of something reacts, how many molecules react, counting in the typical way just is not feasible for counting atoms and molecules. Because the number that we can count of molecules is like not a number that we can see. Anything that you are dealing with on the macro scale in the lab that you're like taking a scoop of a chemical to react has absolutely huge numbers of particles in it. So we count groups of atoms instead of individually. So this is a fairly familiar concept in your life. It just feels a little bit different here because we're dealing with such big numbers. So we group things in life all the time. We sell eggs by the dozen. You don't go to the grocery store and buy one egg, you buy a dozen eggs. What else do we have? You buy printer paper in reams. A ream is 500 sheets of paper. So we are used to these ideas of grouping. This is the same thing for grouping a very large number of quantities, a very large number of molecules. So in chemistry, instead of a dozen molecules or a ream of molecules or whatever other grouping term you have, we have what is known as the mole. We count moles of particles or moles of molecules. So the abbreviation that we use in science for the mole is not really much of an abbreviation. It is MOL, but it is important that you write MOL. Really common mistake I see is that people abbreviate mole as just M. M actually comes to stand for quite a few different things in science, but mole is not one of them, and that is why mole is different, is MOL. So it's not really much shorter. You're saving yourself a whopping one letter. But if you want to abbreviate mole, MOL is correct, not just M. So what a mole is a measurement of quantity. It is a group of things. It is functionally the same as a dozen, and I cannot stress that enough. When we refer to a dozen, it is understood that we mean 12 of whatever we're talking about, whether it be a dozen eggs or a dozen cookies. We say a dozen, we mean 12. The same is true for a mole. It's just not 12. It's a much bigger number than that. So 1 mole of something is equal to 6.02 times 10 to the 23rd things, whatever you happen to be counting. Atoms, molecules, you could technically have a mole of cookies. It would just like cover the entire Earth. And I'm not even joking about that. Not really an exaggeration. So 1 mole of anything is 6.02 times 10 to the 23rd items of whatever you care to count. This quantity is known as Avogadro's number. Avogadro. A scientist by the name of Amadeo Avogadro was the guy who came up with this concept of sort of an easier way to count things. It is technically defined as anything, the amount of a substance that has the same number of particles found in exactly 12 grams of carbon-12 is where this number came from, is the definition. You don't really specifically need to know that. You just need to be able to use this number. So Avogadro's number, commonly symbolized capital N with a subscript capital A, is 6.02 times 10 to the 23rd. So we can use this as a conversion factor between moles and number of things. So if, for instance, we wanted to calculate how many atoms are in 1.5 moles of magnesium. We can do that using Avogadro's number. Just like there are 12 things in 1 dozen, there are 6 times 2 to the 23rd things in 1 mole of something. So our things in this example is atoms of magnesium. So we just need to use our conversion factor of Avogadro's number. So 1.5 moles of magnesium. 1 mole is equivalent to 6 times 10 to the 23rd of whatever we're counting. So we want our units to cancel, which means my 1 mole is going to go on the bottom. And then my number of atoms is going to be Avogadro's number, 6.02 times 10 to the 23rd atoms. Magnesium goes on top. So when we have it set up this way, moles cancels with moles. We are left in units of atoms, which is exactly what we are looking for. And we get about 9.03 times 10 to the 23rd atoms of magnesium are present in that sample. So let's do another example. Let's do how many moles is, let's say, 2.64 times 10 to the 22nd molecules of CH4. So take a minute, pause here, and try to do that one on your own. So for this one, we're going to use a very similar process, but we do need to recognize that we're doing the conversion sort of in the other direction. That in the previous example, we started with moles and ended up with number of atoms. Here we're starting with number of molecules, and we want to end up in moles. So we're just doing the same conversion in the opposite direction, essentially. So we are starting with 2.64 times 10 to the 22nd molecules. There are 6.02 times 10 to the 23rd molecules in 1 mole. So in this case, Avogadro's number is going on the bottom because we need units of molecules to cancel molecules, because we're looking to end up in moles. So make sure you're always paying attention to your units to figure out whether you are multiplying or dividing by Avogadro's number. So I strongly recommend when you write out your work that you do include units, because it can help you make sure that you're following the dimensional analysis correctly. So much of chemistry is really just dimensional analysis with perhaps new and strange units. But if you are good with dimensional analysis and understanding canceling out units, chemistry gets a lot easier. So in this case, we can see that in our units, to get molecules to cancel, we need Avogadro's number to go on the bottom. So we are going to find that we have about 0.0438 moles of CH4 in that sample. So note that when we're converting between molecules and moles or atoms and moles, in these examples, it doesn't really matter what the substance is. Our conversion factor is still Avogadro's number, because no matter what substance you're dealing with, there's always 6.02 times 10 to the 23rd things in 1 mole of that thing. So it's always the same conversion factor regardless of what substance. Magnesium versus CH4 didn't really make a difference in our calculations here.